Okay. So we have our state space, which is which is all of the states that you could possibly be in. Then we have our initial state. Hello. So we have our initial state, which is where the algorithm starts at. That's a terrible color. Okay, so initial state, where the algorithm starts at. Goal state, which is where the algorithm ends and returns a result. There can be more than one of these, so if it just gets to basically any goal state, then the algorithm will stop. Have our state space, which is all of the states that you could possibly be in. This is pretty large for any considerable problem. Then we have our actions. So an action is per state, right? So your list of actions will change. That's why it's represented as a function where you have actions, put in your state as a parameter, and it gives you all those actions. And if an action can be done on S, we say that it is applicable in S. Then we have our transition model. So this is another function with the state that you're in and then the action. And then it says what state you'll end up in. So the result of being on floor 3 of the library and going to room 303 is that your new state is room 303. And then action cost function. So this is a combination of... Yes.
Which algorithm are you talking about?
This is all search algorithms.
Okay.
So this is terminology that we're going to see in every search algorithm.
Okay.
So then this is the action cost function. So we have the state that we're currently in, the action we're taking, and then the state that it takes us to, and that gives us the cost. So in most computer science depth first search, for instance, each traversal is a cost of 1. You're going to one child. But let's say the graph that we're searching on, the edges have different weights. And in that case, whatever edge you take would determine the cost.
So the transition function takes a state and an action and returns a state?
It takes a state, or the transition function, yeah, it takes a state and an action and returns a state. Yeah. All right. And then we have different terminologies for how we talk about different paths. So for instance, if we have our initial state here, and then each edge is an action getting to a different state, then the shortest path, so this is the lowest cost. It doesn't necessarily mean the number of moves if the cost of each move is different, but the lowest cost, that is our optimal solution. Any solution that is not the optimal solution, or really any solution in general, anything that gets us to a goal state, could be more than one, but anything that gets us to a goal state, that is a solution. The optimal solution is a solution as well. And then a path, that's just a series of actions. So if you have an edge that's taking you to a different state, that is a path. It does not need to conclude anywhere. It doesn't need to take you to the goal state. It can just be a path. Okay, time complexity calculation variables. When we're talking about these algorithms, they're typically exponential. They have a lot of different factors in them. And so these are in the time complexities that we'll be presenting. These are the time complexities that we're going to see. So branching factor, this is the average number of actions applicable for a given state. So going back to our 3x3 slot sliding puzzle, for instance, the average branching factor is going to be anywhere from like 1 to 4, because you can slide in any direction, left, right, up, or down, but then there's some in the corners, so they might not be able to move. So the branching factor probably is somewhere like a 3 point something. The input size is typically the number of variables within a given state. So for a 3x3 grid, there are 9 slots, so n equals 9. But just like a heuristic, the input size is something that's going to change depending on your data. So this is the best example, but input size can mean a lot of different things. And then max depth. Max depth of the search tree, basically how many actions down is it possible that we can go. Typically max depth is an incredibly large number. Same thing for input size. Branching factor is something that may be a little bit lesser. Okay. So measuring performance. So an algorithm, a search algorithm can be measured on a lot of different metrics. These are our most popular ones. These are the most important ones. So the first is completeness. Is the algorithm guaranteed to find a solution if there is one, and to correctly report failure when there is not? That is really important. A lot of algorithms, completeness is almost always not satisfied if your state space or if your search tree is infinite, because how are you going to, basically? It depends on the conditions of the problem sometimes. So for instance, Depth first search is complete on a finite acyclical search tree. But depending on how much you change the problem, if the search space becomes infinite, then it's not complete. So this is both a factor of the algorithm and of the problem. Cost optimality. Does it find a solution with the lowest path cost of all solutions? So for instance, breadth first search on a finite space is cost optimal. And clarification, if every action costs the same amount, because it goes layer by layer, which means that each additional layer is just a static addition to the cost. But depth first search does not do this. Depth first search goes left to right. Greedy algorithms will not do this. They will find their first goal state that they can get to by whatever metric possible, and then they will return that goal. So cost optimality is actually slightly more rare than you'd think. Time complexity, how long, this is basic O of N, analysis of algorithms, data structure stuff. How much time are we using and how much space are we using? And these are typically measured in some of those variables that we were talking about on the last slide: branching factor, input size, max tree depth, and also D depth of goal, which is used a lot. Usually D is going to be less than M. That's not guaranteed. Okay, and then finally, graph search versus tree search. This is a really important distinction where graph search, it remembers all visited states, and then if the algorithm is going to go to a state that is already visited, then it's going to skip it. This is going to be high on memory because every state that you get to, you're going to need to store in memory. And then it's also low on time because it makes sure that we are not going to repeated states. Also, just in case you're taking pictures, it's super cool if you take pictures, but I also will post these slides just in case. So yeah, no worries there. Welcome. Then tree search. So this does not remember visited states, and it's going to go down redundant paths, but it's also low memory, high time. The thing with a lot of search algorithms, especially with the sort of games that we're doing here, is that we're going to have crazy numbers of states. So almost always, tree search is going to be AI. Dr. Mitra talks about this in his slides. Basically, all AI is going to be tree search because we're dealing with data sets that are just incomprehensible for a graph search. Okay, so now we can actually get into talking about our blind search algorithms. So the first one, breadth first versus depth first search. This is typical comp sci. You guys probably know this. Just in case, for a reminder, I put an illustration. So our black lines here are like tree relations, and then the red lines here is the control flow. So you see breadth first search goes down and then over to the side, and then down and over to the side and over to the side. Depth first goes down this side, and then from there goes left to right. Okay, pop quiz. What metrics will we use to compare breadth first search with depth first search?
Oh, okay.
Thank
you so much.
Yeah.
Professor Sheldon. I would say time complexity and memory usage.
Okay. It's 2 out of 4, correct.
There's 4. Okay. Should I mention 2 more?
Yep.
Completeness and optimality.
That's correct. You get a check mark.
Okay.
Correct. Yeah, so that's going back to our slide before, how we're comparing the search algorithms. Completeness, cost optimality, space complexity, and time complexity. So that's how we're going to compare these as well. So breadth first search versus depth first search. What are we looking at? For completeness, yes, breadth first search. If the goal exists, BFS will find it. Yep, it's taking up a lot of memory, but it will get to it. It's not going to miss stuff. Depth first search is complete if the state space is finite and has no cycles, because depth first search is going to go down as soon as possible. If you have a node that leads into a cycle, it will continue to follow that forever if you don't do any sort of cyclic detection. Of course, with all of these constraints, there's going to be different implementations that fix, different attributes at whatever costs. For this, we're basically considering the simplest, most standard versions of these algorithms. So depth first search, yes, if state space is finite and has no cycles. Cost optimality, because breadth first search, if all actions are the same cost, because it goes layer by layer, we're going to get that most optimal solution. And depth first search will not do that at all. It will just return the first solution found. All right, time complexity. For both breadth first and depth first search, it's going to be the same time complexity because at the end of the day, they're both traversing a bunch of nodes, and they both have the possibility to traverse the same number of nodes. Say you have a search tree with no solution, and they hit all the nodes, it's going to be the same number because the tree is the same. The only difference is our traversal strategy. So space complexity, because breadth first search is a graph search, it's going to be remembering all the nodes that it goes to. So because it can go to O of B to the power of D nodes, it's going to store O to the B of power of D nodes in the worst case complexity. And remember that B is the branching factor and D is the depth of the goal. And then for depth first search, basically what it's doing as it goes down the search tree, it's just remembering what node it came from so that it can go to the next node. So we're not going to be storing the whole tree in memory. We're only going to be storing as many nodes as the depth of the level that we're currently on. So that's why depth first search space complexity is O of M, where M is the max depth of the search tree. Because if, let's see, our search tree looks like this. And depth first search is going to go down this way, and let's say it's on this node. The only nodes it's actually going to remember are this one, and this one. And then it will go back up, say it deals with this, goes back up, and it's going to go back down this way, and it'll remember that one. And so that's breadth first search, graph search, depth first search, tree search. It will go to redundant paths. And then just because he has quizzed on this, breadth first search does use a queue, and depth first search uses a stack. So actually the analogy he uses in his slides I really like for the queue, where it's like in a line like this, and then as you push it, this one like falls off as you push one on here. So it's a good visualization for a queue. And then for stack, you've probably heard it before, but the plates analogy is really good, where you stack a plate on top of each other, and then as you take a plate off the stack, that was the one that was most recently put on.
Why is that? Why use a queue for breadth first and a stack for depth first?
So with depth first search, because the first one that you put on is the first one that you take off. So let's say at depth first search you go to this one, then you add these two children to your stack, and then you take this one off, and then it adds these children to the stack. Because these children were added most recently, those are the ones that are going to be taken off. So stack is just a way to ensure that we do depth first, where breadth first search just makes it to where the order that we discover them in almost is the order that we go down. And because we're going from the top of the tree down, it's going to go layer by layer. So that's why those data structures are used. All right, so in computation, memory is a larger issue than time. This is Dr. Mitra's view on things, so that's what I'm putting in the slides. This is because memory complexity is bound by time complexity, so memory becomes a bottleneck. So DFS is preferred in general. Like I said, with AI, we're talking big trees. So we can't afford to stick all of it in memory. We can't afford to take the time. So depth first search is preferred in general. However, DFS can get stuck at an infinite or large enough to where we'll never complete depth. So one strategy to apply DFS is to limit the range of it, how far it's going to go. So this is depth limited search. So it stops DFS at a fixed length L, no matter what. If in the actual pseudocode of the algorithm for each algorithm or for each node that it gets to, if it's on a node and it checks and the depth is larger than a variable L, then it just returns. So it's an incomplete algorithm. Obviously, if the depth of the goal is larger than the depth that we go to, then it's not going to find it. But we do get a decreased time complexity. So with regular depth first search, we have O of B to the D, and in this case, with L, we kind of limit that. Or O of B to the M, where M is the max depth of the search tree. Sometimes they switch up what variables they use, but basically depth first search can do the whole tree. This cuts off a lower part of it. And of course it only remembers as many nodes as how deep it goes. It will never go deeper than L. So we have O of L memory complexity in the worst case. Okay, iterative deepening search. So the idea behind this one is that finding a good value of L is actually really hard, and adding more to L, like repeating iterative deepening search from an O of N complexity, is actually not that expensive. So the idea is that we iterate through L. We start with 0, and then we go to 1, we go to 2, and we keep going until we find our goal. In this example, there's not really a goal node, but you see we basically extend how deep we're going down the tree. So it is complete because when L equals D, we're going to find our goal. And then the cost complexity is O of B to the D plus 1. So the last layer, which is where the goal is found, because we're going deeper and deeper every time, it's kind of like breadth first search, where we're going layer by layer, in a sense. So in the last layer, where the goal is found, it's going to have B to the D nodes, and it's explored once. And the second to last layer has B to the D minus 1 nodes and is explored twice, because we will have L would have equaled D minus 1, and then so we would have computed all those nodes, and then L would have equaled D, and so we have computed all those nodes again, and then computed the last layer of nodes. So we get this little formula here, N for IDS, where basically you see there's a sliding scale from D to 1 in the coefficient, and then sliding scale from 1 to D in the exponent of B. Does that make sense to everyone?
I'm kind of lost.
Okay.
So the point of this search is to like increase the layers that we're checking. Okay.
Because the idea is that in regular limited or depth limited search, you can set L as less than the depth of the goal, which is a problem because that takes away it being complete.
Yeah.
And so with this, we will always find the goal.
Okay.
And the idea is because of this evaluation, we're actually not adding too much to the time complexity, so we can afford to repeat. And I think in Dr. Mitra's slides, he said for one example, this led to like an 11% cost increase, which isn't terrible for the guarantee of completeness.
Okay. Okay.
So what do you define as, is this time complexity cost? So what do you define as cost in this scenario?
So cost is the number of nodes we're checking. So number of children we're traversing. And then memory of complexity is still O of D, because it's a complete algorithm. We will get to the goal. We're never going to explore deeper than the goal because of the increasing depth. So we're only remembering D nodes maximum, where D is the depth of the goal. Okay, so we're going to go ahead and do the first question on the quiz, which was an application of IDS. So an important note here, L equals 0 in every implementation of iterative deepening search. In that case, we would visit A, and that would be the end of the algorithm. So I talked with someone who's taken Dr. Mitra's class before, and he says that Dr. Mitra just doesn't do that he just doesn't visit the first node on the first iteration because reasons. So it doesn't get put in the visited array, but I want you to know that in every sane implementation of the algorithm, A would go into the visited array, but we're not doing that. So L equals 0, so that would be the first node, first layer, and then A, we can't investigate its children because they're too deep down, so we increment L, and then we run the algorithm again. So visit A, add all of its children to the queue. So now our L is 1, so we're going to go to these first two layers, and so we're going to add B, C, and D, and we're going to visit all of them, but we're not going to add their children because they're too far down. So we go to B, and remember we have no heuristics, so we're going left to right as a default control flow, but on the quiz, Dr. Mitra did specify that on the quiz. So we visited A, B, C, D. Maximum depth reach, no more children. Everyone on board? Okay. All right, so we're starting the algorithm again. We start the same way that we started on L equals 1, where we go to A, add to the queue, we visit it, add all of its children, B, C, D. This time, though, this layer is within the children that we're seeking. So when we go to pop B, we add its child, E, to the queue. And remember we add it to the stack, more accurately. So I guess this would be a stack. So careful of that. That's a terminology difference. So E would be going first because it's the most recently visited. So we pop E from the stack, and then E doesn't have any children, and even if it did, the depth would be too low, so we don't go to it. So next is C. So we add F and G to our stack. Go to F, no children. Go to G. J is too far down, so we don't go to. And then we go to D. D has goal as its child, so it's add to the queue, correct depth, goal, and we have our solution. Any questions?
So, what? Okay, I'm kind of confused because this algorithm seems similar in terms of like traversal with breadth first search.
It is breadth first search, line by line.
Okay, but we're increasing the length or the depth of travel.
Basically.
Mm-hmm.
Okay,
So
okay,
it's breadth first search, but you go one line at a time.
okay.
Yes.
Except the only difference though is that it's like you wouldn't store all the nodes inside the queue like with breadth first search. That's why we'd use the silver BFS because it does still reduce the memory.
That's why you're popping that.
Yeah.
Okay. Okay.
Yeah, so one other thing is that within each iteration of L, it is depth first search. So we went ABE, and then CF, and then G. We're processing the deeper nodes as fast as possible because in breadth first search, it would be A, B, C, D. We're not doing that. We're going ABE, CF, CG, D, and then goal. However, in the broad scope, it emulates the behavior of breadth first search because we're going layer by layer. We're going deeper every time. So it's almost a combination of the strengths of breadth first search, where one of the strengths of breadth first search is that you never explore beyond the depth of the goal. So iterative deepening search does that as well. However, it also takes some of the strengths of depth first search where we're not memorizing everywhere we've been. We're just going to, as deep as possible, try to find something and go back. So this is also a concept of intro to analysis of algorithms where we have a difference between pure algorithms and then I guess more complex algorithms where by taking features from different algorithms we can improve efficiency and customize our algorithm for the problem at hand. Okay. Any questions before we move on about search? Okay. So we're just going to be doing the guided best first search because I ran out of time. I worked on this presentation for like 5 hours, but I still only got like 45 slides. So this is just going to be a quick crash course on some of the early concepts, and then on our own we can just kind of share materials as we're studying. I do actually have a couple of things that Dr. Mitra has said in class that will probably be on the exam that I'll send to you guys. But heuristics, adding things to your search to try to not just pick randomly. In breadth first search and depth first search, you're not really picking randomly, you're picking in a determined order. But the point of heuristics is being smarter about what we pick, making educated guesses about what state to go to next. So with our heuristics, we have our heuristics function f of n. Now, what f of n is actually composed of depends on your algorithm. So for instance, in A star, f of n equals g of n plus h of n, where g of n is the distance of the path so far, and h of n is the heuristics guess on how good this next node is going to be, whether you should go to it. So we are trying to minimize f of n. So in the vast majority of implementations, minimizing our heuristic value is the best option. So making educated guesses about what state to go to next, best guess on how far that next state n is from the goal. So because we're trying to get to the goal as fast as possible, we're trying to not repeat too much, we're trying to just take a path, which you can also see how without much change, heuristics is a greedy approach. Of course, there's things you can do to circumvent that, but which is we get into. But we're trying to minimize the distance from the goal. And then the informed search algorithms run f of n on states made available by actions and pick the state with the minimum f of n. So we're minimizing. Okay, greedy breadth first search, or best first search, more accurately. So this is using a heuristic. At each step of breadth first search, we are using the heuristic to educate what order we go in for nodes. So remember, because this is a modification of breadth first search, which is kind of easy to memorize because the acronyms are the same and they sound so similar. But this is a graph search, so we're remembering all the places that we've been to. It's just that Q that we used in breadth first search, we're replacing that with a priority queue, where the key is the value of the heuristic function for a state. So we're going best heuristic first for how we process our nodes. And assuming this graph search, it is complete within a finite space, and it has a b to the power of m time and space complexity. Okay. So this is the question for search quiz questions 2 and 3. I think question 2 asks you the contents of the priority queue after iteration 2 or 3. And then the next question just asks you to do the visited status. So I just turn them into one demonstration. So our first node that we go to is A. And we don't have any limits on depth or anything like that. So we're just going to add the children B, C, and D to the queue. This is not left to right, obviously, because C5 is less than 6, which is less than 9. We order C, B, D. So the first one that we're going to go to is C. So we pop it from the queue, and then we add it to children. And then we, as a queue typically implemented with a min heap, we basically reorient the entire queue each time we add new things to it. So we see F is 4, is less than 6, is less than 8, is less than 9. So we have F, B, G, D. So the next node that we're going to pop is F, which doesn't have any children, so that doesn't change anything. Continue to go to the next node, B. So we have that. Then we add E to the queue, and 7 is less than 8, which is less than 9. So E is the next node that we go to, and it has no children. Next is G. And we have J here. So it has a child, it gets added to the queue. 1 is less than 9. And so we have J. Yep, which we visit that, doesn't have any children, so the only thing left in the queue is D. Pop that, D. And then we have our goal. That's the only thing left. It doesn't have any children. We pop it, and then that gives us our solution in the visitation order. So one thing to note here is that heuristics at the end of the day are just a guess. So if you actually just did a standard breadth first search here, you would have gotten a lower cost complexity on this particular tree. So heuristics have a couple of different criteria that kind of ensure quality in a sense. So an admissible heuristic means that the heuristic value of any given node is always less than the actual distance or the actual value of that node. So an yes?
When you go ACF, when you go to B, but you don't go back C and A before going to B, or you just don't write it because it's a set instead of a list?
So it's a queue, so we're not necessarily kind of as we pop each one, we're adding those child nodes to the queue. So each node is kind of processed independently. It's not like we're doing a for loop on each layer where it's A, and then it's like for each child, then we execute. That would be a recursive algorithm. With a queue implementation,
So you can just jump around, so you just go straight to whichever node you're looking for.
Yeah, so if I'm A and then I add C to the queue and I add F to the queue, okay, depending on your heuristic, I guess you could jump from like A, C, F, E, D. You can jump all over the place depending on what the heuristic value is. So admissible heuristics are pretty good. Basically, the idea with admissible heuristics is that you're always undershooting the actual distance. But the closer that you get to the actual distance, the more accurate the heuristic is, the better. And then there's also the higher bar for heuristics, which is a consistent heuristic, which means that it is never going to take you down the wrong path, which is a very high bar that a lot of heuristics just can't reach. But as you can see, a heuristic it's not necessarily going to improve your route on all data, but you want to derive heuristics that do. This is a case where, in most cases, a heuristic would be useful, but because of the heuristic values chosen, it's actually less efficient than breadth first search. But that is all I have prepared. So the rest of that we can do on our own. I'm gonna send these slides in the Discord, and then let you guys know some exam questions that he said in class that he'll put on there. But any questions? Nope. Cool.
Don't forget beam search, guys.